This is the digital multimeter that comes with your toolkit. The name digital multimeter also is short, you can refer to it as a DMM, but the digital name comes from the fact that it has a numerical display as opposed to an analog meter, which has a needle that deflects, and then you interpret the position of the needle on a scale. So it's a low-cost DMM, but a decent one anyway for the price. In the $50 range, it still has okay accuracy, and it'll certainly do everything we need it to do. As far as getting a level meter that you'd be shooting for out in the field, you'd probably want to spend a little more, a lot more, probably like $300, $400 would be the price point to get something that you would use in the field. But this is perfect for learning the basics of electricity, and the 2 years that you spend in your studies with electronics, it'll work fine for us. And we'll see some of the shortcomings as we go through exercises. I can sort of point those out and let you know what the more expensive meters would do a better job of. I know we looked at it a little bit when we had the breadboards to set up. So if you remember, this orange case can come off, and then there is that screw in the back. And in fact, we put probably better quality batteries in. I mean, the ones that ship with it, you might just toss them in the trash and put something decent in there. If your batteries do run low, you can watch for a battery indicator on the screen. Keep an eye on that. If that battery indicator shows up, the readings could start to be inaccurate. So you want to replace the batteries. We also mentioned these fuses are sitting in here, and those are for the ammeter, because what happens is when you use it as an ammeter, you actually have to get the circuit current to flow through the meter. So they are a way of protecting the meter from overload, because it does become part of the circuit. You have to actually open up the circuit, put the meter into the circuit, and that makes it a little bit vulnerable. If you didn't have fuses that could protect it, you could damage the meter. So we have a 500 milliamp fuse that protects the low scale ammeter readings, and that would be when you're doing current readings, running current into this jack. This path, it would be conventional current would come in here and out here. We'll get to that in a minute, but the 500 milliamp fuse protects this path, this jack, as you put current into the meter and try not to overload it. And then there's the 5 amp fuse here will protect higher current readings, which you use this jack for those. So when you're flowing current in here, the path is protected, the meter's protected by a 5 amp fuse. It does say you can measure up to 10 amps, and that might make you wonder how that's happening. But if you look, there's probably a note somewhere, and it'd be in our manual if it's not here. They're going to tell you that you can do 10 amps for 30 seconds maximum. So they're telling you that fuse, it can carry 5 amps all day long. It can carry 10 amps for 30 seconds, but they're giving you this little note to say that if you try to run 10 amps through the meter to measure it, don't do it for more than 30 seconds. And after you've done it, if you've done it for 30 seconds, allow 15 minutes for that fuse to cool down. Fuses are just, heat that melts them. So it's got to cool down if you want to do another 30 seconds. So, but the manual that comes with the meter can answer little questions like that for us as they arise. But when I see that 5 amp fuse, I know I can carry 5 amps all day long. I can measure 5 amps. And if I do a quick measurement, I can do up to 10. Okay, so that's just a little look at some of the stuff. I know we had looked at that before, and I'll put this back together. We'll talk about some other things. And also just a quick review. I know we mentioned this before too. We have probes that ship with the meter. It's banana jacks that go into the meter, and the common's in the center always. And then if you're going to measure things like volts, milliamps, microamps, you're here. Over here, this jack is only used to measure high currents. So you put it over there for that. And we have the other end of the probes. In this case, you know, these are probes, and they have little shields if you want to get into tight spaces without shorting things out, or these can pop right off and you have the full exposure of the probe. So that's one option. Another one that's really nice, again, banana jacks on the one end and then mini grabbers on the other end. So you just press these in, and they're little hooks that can hook onto things. So they can hook onto a wire or something like that. So that's a useful thing. And these are all coming with their own length of wire. And then for probing around on a breadboard, we have banana jacks that are on the other end. There's these little pins, you know. So those are some options. The goal of any good measuring instrument is to not mess up the thing you're trying to measure. So keep that in mind, and we'll show you sort of how the voltmeter is designed, how the ammeter is designed, how the ohm meter is designed. What we're going to try to show you here in this video is at least how to measure voltage, how to measure current, how to measure resistance, and what your meter looks like when it's in those modes. To measure voltage, we already introed this a little bit. You have a selector switch, and you would just go to the volts DC. Volts AC, well, that'll be later. Right now we're just using DC voltage, and some of you might or might not know what AC is even. But volts DC, that's direct current. That's current that doesn't change direction. And that's where we're going to be for these weeks. And the display will display a number that shows you the difference in voltage between the two probe points. So wherever you put these, the difference in voltage between those 2 points will show up. So what's the difference between these 2 points on my whiteboard? Not much. It's kind of, you know, not much voltage there anyway. How about from my left hand to my right hand? I wonder what the voltage is. Okay. And I would say my right hand, well, I had 30 millivolts difference, you know, but it varies, of course, because I'm, you know, it's not exactly a conductor or any kind of circuit. But that 30 millivolts that showed up meant that my right, it was positive. So it meant my right hand and left hand, there's 30 millivolts difference, and the right hand is actually more positive at the moment. That changes all the time. So the point I want to make is that if you that the number showing up in your screen shows the difference between the two probes, but it also shows if it's a positive number, it's telling you the red lead's more positive. If it's a negative number, it's telling you that the point that the red probe is at is more negative than the black lead. So it always reads the voltage at the red lead with reference to the black lead. It's another way to say it. But that's important so that you understand what that little negative symbol means. So again, if you don't see the negative symbol, you have a more positive voltage at the red lead. So for example, my voltage source, I could just poke around, and that's the thing with a voltmeter. You're okay to just poke around with a voltmeter. Not so with an ammeter. We'll get to that. You have to be more careful with that. But an ohm meter, I can bring it here and I would read the voltage, and it would show up as a positive voltage because the red lead's at the voltage is more positive at the red point, red lead, where the red lead is. And by a certain amount, and that number would show up and it'd be a positive number. Of course, if I put the red lead here, then I'm asking, what's the voltage look like here at this point compared to over where the black lead is? And the answer would be, again, you know, if it was our little 1.5 volt battery, it might be 1.5 volts, but it would be negative 1.5 volts because the red lead is actually sitting at a point that is, yes, a different by 1.5 volts, but it's 1.5 volts more negative than the point where the black lead's sitting. Okay, so you can poke around with the voltmeter and you won't get in trouble. You can just probe anywhere. I mean, I could put the black lead of my meter right here, you know, and I could check the voltage that's developed across this resistance. You know, as current would be running, maybe I have a closed switch here in this example, current would be running and there would be some voltage. There'd be some backed up pressure here as it hits this resistance. What is that voltage difference from this point to this point? I mean, this point would be considered downstream where the black lead is here, and this would be upstream, and there'd be some where conventional current enters the resistance, there would be some backed up positive charge. So I would expect to see a positive voltage difference from this side to this side, and the voltmeter would show me that. What voltage is my lamp getting, you know? and so on. Is there much voltage across the switch? Probably not, because there's not much resistance there. So for any current that's flowing, Ohm's law says current times resistance is voltage, and there's not much resistance, hopefully, if the contacts are good. So just some quick examples. Don't worry if you're not following those exactly. We'll definitely get good at all that kind of stuff. So we'll really understand those concepts down the road. But I could look at different points in the circuit with reference to this point, which might be sort of my circuit common if I want it to be. I could go looking around at different points in the circuit. I could look at component voltages and so on. But that's gets you the idea. You can look at any voltage. Just put the 2 points down at the 2 points of interest, and the meter will tell you the difference in voltage between those 2 points. And in fact, also which side is more positive than the other one. I want to get back to that statement that a good instrument, when it tries to measure something, it's important that it doesn't mess up the thing it's trying to measure. And I want to see if we can understand then the design of a voltmeter. So let's say I was going to put a voltmeter. We could just put a little circle. That's my voltmeter. And I'm going to connect the voltmeter across the lamp. And that's how you would always do it. I mean, voltmeters always, people maybe remember, they go in parallel with the thing that you're trying to measure. And if you look at this voltmeter being connected here and here is how I'm going to measure the voltage that sits across the lamp, or the voltage difference from one side of the lamp to the other. And the question is, how can we design that voltmeter so it doesn't mess things up? So to answer that, let's look. What would the ideal voltmeter have? Would it be a very low resistance path? No, because low resistance, if this voltmeter had very low resistance, current would just run around the lamp. You would have altered the circuit. You would have messed it up. Think about it. How will that voltmeter essentially be invisible to the circuit? So in other words, it doesn't have an impact on the circuit. It doesn't mess things up at all. The ideal voltmeter would be like an open, infinite ohms. You know, we would love it if we could make a voltmeter that was infinite ohms. We can't quite get there, but the thing I want you to impress upon you is the higher the resistance, or really we call it impedance because it's more of a complex resistance, but we can call it resistance for now. But the higher that is, the better for a voltmeter, because then when you do touch the probes to these 2 points, you don't divert any of the current around here. So we would love it. We can't get to infinity, but good voltmeters would have something, you know, in the order of maybe 10 megohms, 10 million ohms. Maybe, I don't know, ours might be there. Ours might sit more in the 1 megohm realm. We can check the manual. More even, I mean, so maybe a couple $100 you'd spend, you'd expect to have 10 megohms at least. You start getting upwards, you know, more towards the $1,000 price range or something. You can keep pushing that higher, you know, 100 megohms, even a gigohm or something. So, but you'd pay more for it. But the higher the better for impedance for a voltmeter. You really want that to be essentially invisible. And like we said, how do you see the invisibility of a voltmeter? Well, obviously, if it was like an open, it would not do anything to alter the circuit as you put it across different points. So that's the thing I wanted to emphasize. Your voltmeter is going to be really high resistance, high impedance would be another word that we actually use. And that also kind of explains why you can not get in trouble when you're poking around. I mean, it's not too worrisome. I can just put these probes anywhere I want. It's definitely the troubleshooting instrument of choice for that reason too. I can probe a circuit and I'm essentially not connecting anything to the circuit. I mean, I am, and we have to always remember the truth of that is that we are connecting at maybe a 1 megohm or a 10 megohm or a 100 megohm resistor, you know, which is the voltmeter itself, to the circuit when we do that. So keep that in mind, because when we probe high resistance circuits, they do, the voltmeters resistance is significant. Here, in a low resistance circuit, like a lamp with like a 10 ohm or a 100 ohm resistor, for example, the 10 megohms isn't going to alter that circuit very much. We'll get back to that concept, but I just wanted to introduce that a voltmeter, you know, the higher the resistance, the better, and you're not going to have too much trouble poking around a circuit with it for that reason. Now, an ammeter is exactly the opposite. So let's take a look at that. And if we wanted to do a current measurement, now we do have to be careful. It's very easy to blow a fuse. You actually have to divert the circuit current through your meter so that it can measure the current. But to do that, we're going to take the selector switch and we can pick a scale here. Are we going to be down in the microamp range or milliamps? If so, you're going to be using this jack right here. If we need a high current, then you would move this over to the 10 amp scale. Now remember, we have fuses in there to help protect the meter, but it is easy to blow a fuse if you hook the ammeter up incorrectly. Later when we do the ohm meter, I'll try to remember to tell you, you can use an ohm meter to check to see if the path for your ammeter is still intact. In other words, to check for a blown fuse, you can use an ohm meter to do that. So, or if the fuse blows, it'll be an open and your ohm meter would read that as such. So let's put it on the milliamp scale perhaps, or I don't know, let's go for the 10 amp scale. Why not? If you don't know the current that you're going to be seeing go through your meter, better to start high and work your way down. So there we go. And now for an ammeter, we said you actually have to break into the circuit. You actually put the ammeter in series with the circuit. So an ammeter is going to be requiring that you open up the circuit. So let's say I wanted to measure the lamp current, and let's just get some current here in our little drawing, right? So current, we'll learn more about this when we get to series circuit and circuit analysis, but I have some voltage and I have a complete path, so I have current flowing. And in fact, there is only one path, if you can see that. So there is only one current. So it's not a real complicated thing. As far as measuring current, I don't care where I break into the circuit. I can insert my ammeter here or here or here or here. Doesn't matter. It's the same current flowing everywhere. And when I say insert, let me show you what I mean. I just have to physically open up the path and get my meter in there. I mean, we would do it schematically like this. We would just put the little ammeter symbol in there, and that means your ammeter's in there. Let me show you another literal thing so that it might help some of you if this is all brand new. So I would open up the circuit, and what I would do is take my probes, and I would say that the current now is going to flow. There, I complete the circuit. I open it, and then I complete it with my ammeter. This would be how it would be done. What's going to happen is current's going to flow through the red lead, through my meter, out of the meter, through the black lead, back to return to the circuit. So I'm actually taking a look at the circuit current by making it flow through my meter. I'm inserting my meter into the circuit. Okay. It doesn't matter where I do that in this circuit because it's just one path. It's a series circuit. Current's the same everywhere in a series circuit. I could insert my meter here, you know, and it would get the same reading. It would be the same current. Again, I just picked a different spot to insert my meter, okay? But the meter has to go right in series. And that begs the question, what would the ideal ammeter look like as far as its resistance? Remember, you don't want your instrument to mess things up. You want it to be invisible. You want it to act like it's not even there. You don't want it to alter the circuit at all. How do you insert an ammeter into a circuit and have it not alter the circuit? Well, the ideal ammeter then would be 0 ohms. So just the opposite of a voltmeter. So you try to design an ammeter that has basically no resistance, and then when you put it into the circuit, it doesn't change the circuit at all. But that means you can't go poking around with these leads when you have your meter set for an ammeter. And here's a deadly thing just to demonstrate. if I got confused and I said, I want to see what kind of current that power supply has, you'll see high current, all right. You'll probably blow your fuse unless there's some kind of current limiting. If I put my ammeter across anything, it's just shorting it out because the ammeter is 0 ohms, ideally. And it won't be 0, but it'll be close to it. I can tell you on the 10 amp scale, we might be like 1/10 of an ohm, something like that for the meter. So don't be doing that. When you try to measure the current that's going through this resistor, this is not how you do it, right? Not like that. That's how you measure the voltage across the resistor, but to measure the current through it, you better break it open somewhere. I don't care where. Now, I've got the current running through my meter, which is also the current that's running through the resistor. So the ammeter always goes in series. It's an easy mistake to make when you're trying to do both. You know, you just finished, I'll tell you the way people blow their fuses most often. They just finished measuring the voltage, let's say, and then they know they're going to do current next, but they left their leads there and they switched it to current before they switched the configuration of the leads, and that'll just dead short and blow your fuse. So there are ways, and or people that just don't understand what they're doing. That's a common thing, to blow the ammeter fuse. So I think I did include some extra fuses in your parts kit because I know how it goes. I know they get blown easily, especially in the beginning. You can do yourself a favor and stay on the 10 amp scale as much as possible because that fuse is harder to blow. You won't blow it with a little AA battery. It can't push out 5 amps or 10 amps. So that's a smart move to keep it on the high scale. When you get down to the milliamp scale, that fuse is more vulnerable. It can only handle 1/2 an amp. And a AA battery, I believe, could blow that, pretty easily. For our meter, when you do go onto the lower scale, like milliamps, it starts moving away from that 0 ohm ideal pretty quickly. It's not a very expensive meter, so I think for ours we see things maybe in the order of 10 ohms. In other words, on the amp scale, the ammeter might be around 0.1 ohms, which is pretty good. That's pretty invisible. When you get to the milliamp scale, though, you'll see you're actually inserting maybe as much as 10 ohms into the circuit, and that's significant. And you'll see this. You'll see the number change. The current will drop a little bit from what it actually is or was. On the microamp scale, for our meter, it's going to be maybe even up to 1,000 ohms that you're inserting into the circuit. And you might say, well, man, that really changed the circuit. But look, if it's a microamp current that's flowing, chances are the circuit's already up in maybe the megohm range, right? So 1K isn't terrible. I mean, it's not great. We wish that we didn't have this 10 ohms and this 1K ohms that we're inserting. But that's what you get, in the $50 meter range. Now, in the hundreds of dollars, this usually can be brought down significantly, maybe closer to the 1 ohm range. So you might have something, better there. And this might be only 100 ohms, So you could probably get down by a factor of 10 if you go up by a factor of 10, right? $50 to $500, that'll do it. So yeah, and you can get meters. Usually they're more the benchtop meters, not the portable ones. But Fluke makes a benchtop meter that actually uses a different scheme, and they use op amps, and we'll know what those are down the road. And they can get very close to the ideal 0 ohms. We'll show you that little cool circuit, but you use an op amp to create sort of the ideal sense resistor. But for another day. So what I've seen over the years is most people don't have trouble remembering how to measure voltage, but then they just try to do that same approach to measuring current, and that's where all the trouble happens. Then they blow their fuse, then they don't have a path, and they can't measure current. So that's one thing I see that's very typical. They forget to put the ammeter in series with the circuit. And then the other thing is that they forget, or some people don't ever know or realize, that your ammeter isn't perfect. I mean, your voltmeter is not perfect either. I mean, you have the 10 megohms that can cause problems. But you also have to always remember that your ammeter is not perfect. When you put it into the circuit, especially on the milliamp scale with our meter, you're putting 10 ohms into the circuit. So you are changing the circuit slightly. And then one other thing that's good to understand, and I'll see if this does make sense to you. It's nice to know. Your ammeter, when it measures current, is really still just measuring the voltage. So in other words, let me see if I can get this across to you. When you set it to measure voltage, yes, the little microprocessor, little computer in there, it's measuring the voltage and displaying that. When you run current through the meter, guess what? It's still just the voltmeter doing the measurement of voltage, but what it's doing is it's measuring the voltage across these sense resistances. So these, I just wanted to tell you where these resistances come from. We're stuck with them because we need them, because to measure current, the truth is you're still just measuring voltage. But what we've done is we've arranged your meter so that the current through the circuit flows through your meter, and inside your meter is maybe, if you're on the amp scale, a 0.1 ohm resistance. Now that's known as a sense resistor, because the little microprocessor that's measuring the voltage, it's going to measure the voltage across the ammeter's little resistance that it knows already is 0.1 ohms, and then it'll do the math and do the calculation. So this is what's happening inside your ammeter. Your when your DMM is set to measure current, you're still measuring voltage. That's what I'm trying to tell you. But it's happening inside. You run the current through your meter. That current going through your meter runs through a specific amount of resistance, and the voltage is measured across that. The voltage that occurs across that resistance is what is measured and then calculated, and Ohm's law is done internally in your meter and displays it as the current. But that's what's really happening. It's measuring the voltage across the internal resistance of the meter that you that you see here. That's why we have those. They're sense resistances inside your meter that we actually send the current through and measure the voltage across and do the Ohm's law calculation and display that current then on the meter's face on the display. That might be more nice to know than need to know, but it does help make sense of the whole system, right? So I like to explain that because it even helps you remember what's going on. It helps you remember that the ammeter does have resistance. It needs to. We need to keep it small so it doesn't mess up the circuit that we inserted into. But we need it there so that we can actually get a voltage reading across it and do Ohm's law and deduce the current to display. So, well, moving on to the ohm meter, here it is, and you can. It probably comes up default mode as ohms. If you hit the mode button, you'll toggle through a couple options there. You can do diode check, you can do a continuity check, we'll get to that in a minute, or capacitance you can measure, and those all show up on your screen. I would say leave it in auto mode. It's going to auto range. So if you see auto, that's good. It's automatically going to pick the right scale. Right now, it's trying to measure the resistance between these two leads. And really, there's only air, and there's maybe a little moisture in the air, but it's going to be pretty high resistance. So it's trying, but it can't get anything. And that's showing me that it's on the megohm scale, and it's still OL, which is overload. It's higher than it can measure. Now, I can measure the resistance from my left arm to my right arm. I can, or my, all the way down to my left finger and right finger. So right now I'm about, 900K, almost 1 megohm. A lot of that resistance is contact resistance with my skin. If I would wet my fingers, I'll do that. I'll do that off screen. Spare you. It's going to lower it significantly. See, now that my skin is wet, it's much less resistance. Now I'm down at 170,000 ohms. So But yeah, the ohm meter is going to just measure the resistance between the two leads. Again, if you want to know the mechanics of that, like what's actually going on, it's actually sending a small constant current out and then measuring the voltage across whatever you put between those leads. So again, it's, guess what? It's still the voltmeter doing the work. So whether you're measuring voltage, current, or resistance, the truth is it's all the same measurement on the inside microprocessor side of the meter. Not that you have to understand that, but it's kind of nice to know. We can do a couple more ohm measurements for examples. Let me get a couple resistors here. And here we have a resistor, and let's see what we've got. Okay, and I'm doing something wrong intentionally. Maybe you might recognize it. So it might take a little while for the meter to, again, on a lower cost meter, this might take a little time, but it's a 10 ohm resistor. I can see that. Now I'm not affecting it much, but it's a bad idea, it's a bad habit to have my resistance also joining the resistance of that 10 ohm in parallel. So I don't really want to be touching the leads. I want at best to be only touching, at least only be touching one lead. Okay, so you don't want to be touching and getting involved in the measurement because you do have resistance too. An even better plan is to use the mini grabber leads. That's one of the reasons that we have those for you. If you're trying to check some resistances but not be, bumping into the thing you're trying to measure, the mini grabbers are great for just hanging on to a component that you're trying to get the resistance of. So let's redo this 10 ohm resistor, see how nice this is. I've got my mini grabbers, and it also gives you a nice stable reading because when I was squeezing there with my fingers, the contact resistance was affecting the measurement a little bit too. So, and there's oxide, so who knows? The resistance can be flickering around. But yeah. So the mini grabbers are really nice. The thing to also remember about the ohm meter, it's doing its own thing. It's putting a little current, a little constant current out through the device to be tested. Basically, it's its own little circuit, which means you cannot use an ohm meter on a live circuit. I could not go in here with current running and put my ohm meter across that resistor. Two rules for measuring resistance, for example, or anything like in a circuit like that. I can't go in on a live circuit. Well, there's a couple things. The resistor's not isolated and there's power there. You need whatever you're trying to measure with your ohm meter, you need it to be all alone, right? All isolated, which also implies that there's no power there. So, but that's very important. You can't go onto a live circuit with the ohm meter. That's gonna wreak havoc on it. And also the thing you're trying to measure needs to be by itself. Otherwise you're gonna get other paths maybe around it that will learn what parallel resistances, how they add, the conductances add actually. So so there can be things that interfere with your measurement. So it's got to be powered down would be something people know, but not just powered down. It has to be isolated, and the isolation actually takes care of the powered down, doesn't it? So the truth is, if I had this thing sitting in a circuit, I could even just pull off one wire if I really needed to see it. It's isolated even if I just take off one side. So, but if you're paranoid, you can totally isolate it, take the whole thing out. But as long as you have one side disconnected, it is isolated. Something to keep in mind with the ohm meter, when you're doing a resistance measurement between these two test leads, for example, you want to try to get the resistance of something. Keep in mind that the resistance of the test leads themselves, the wires themselves, is included in your measurement. So if I just connect my test leads together, I can see there's a couple tenths of ohms. Maybe it's about 1/10 of an ohm per test lead, giving me about 2/10 of an ohm. So if I want to, I could subtract that from my actual measurement. Now, this is kind of splitting hairs, and for a $50 meter, it probably doesn't have that kind of accuracy anyway, so it's not something we really have to worry about. And but it's something to remember. And then the thing is, on a more expensive meter, you might have a zeroing button where you can connect the test leads and then sort of hit the 0 button, which is the same thing you would do to tear a scale, right? So, and there's other things too. If you're measuring resistances that are that low that the test lead resistance is significant and going to mess things up, there's a 4-wire measurement technique, but I won't get into that. But that's another type of test lead you can purchase, and each test lead has 2 wires in it, one to carry the constant current for the ohm meter, and the other one to just come out and sense the voltage across the device under test. So that's a 4-wire measurement. Not that we're going to worry about that stuff. We're not getting down to those kind of levels of precision. And finally, I just want to mention, if you think you did blow your fuse in your ammeter, you can borrow someone's meter, set it to ohms, and then if you have your test leads that are banana jacks on both ends, you simply connect your ohm meter to that person's ammeter, have yours set configured for ohms and theirs configured for maybe the milliamp scale that you think, if you think you blew that 500 milliamp fuse. The ohm meter will test the path that runs through that ammeter. And if the fuse is blown, that means the little wire inside the fuse has melted, resulting in an open, and the ohm meter will show overload saying, hey, there's infinite resistance here, there's an open path through your meter, and that means you blew the fuse. So you can always use an ohm meter to check an ammeter. Incidentally, if the fuse is good, the ohm meter will also indicate that, and it'll show you an idea of the resistance of the ammeter. So the ohm meter can kind of characterize the ammeter's resistance, and at the same time, the ammeter will characterize the ohm meter. The ammeter will read the current, the constant current that the ohm meter is using to do its measurement of the ammeter's resistance. They'll kind of rat each other out. So, so that's interesting. You can learn a lot about your meters. If you have 2 of them, you can use one to sort of show what the other one's doing in those kind of settings. Okay, I think that'll be good for now. I mean, I just wanted to get those basics across, and then maybe I'll do another video where we take some actual measurements, and maybe we'll have like a handout or something. You can go along, work your way through some exercises with your meter and a simple circuit. I think that might be a good video to do next. So, but we'll call it good for now.